my colleague Mr. Siebert and I will give you a short overview about manufacturing technologies developed by the Fraunhofer Gesellschaft regarding manufacturing of electric machines. And the first one I would like to give a short overview is the technology of cast coils for electric machines. I will start with a short introduction about the technology. Then I will give an overview about the advantages of the technology, in special the geometrical, the electromagnetical, and the thermal advantages. Afterwards, I will give examples of the casting process and how we do the insulation process. And I will finish with 2 application examples and a conclusion and an overview about the next steps in our research focus. First of all, what is the motivation to develop a casting process for coil? We all know the requirements on winding of electrical machines. We want to have high slot filling factor, whereas at the same side, we want to have a low thermal resistance to the lamination stack. We want to have minimized current displacement effects, of course, to minimize eddy current effects and additional losses at higher frequencies. And of course, we would like to have an automated manufacturing capability to reduce costs of electric machines. So to us, it came to us that there are limits on the current winding technologies. We are limited in slot filling factor to about 60%. And there are, of course, different technologies in winding. On the one hand, the edge-wound coils we see on the upper side. They offer very good thermal behavior and very low current displacement effects, but they have a relatively large bending radius, so you have an axial length of the machine and local signaling through the bending process. And as an alternative, you can use stranded wire or small conductors in parallel to reduce current displacement effects, but they suffer from very high thermal resistance inside the slot area. So we developed the casting technology, and to us it occurred that it combines high slot filling factor, good thermal behavior, and very low current displacement effects. So how was it realized? We take the coil, we construct it with a flat conductor arrangement, shown on the upper side of the picture. After that, we do a stretching of the coil geometry, add the gatings, and use a casting process. We can use different casting processes. I will give an overview later of the used casting processes. And after the casting, we remove the gatings, do the insulation process, and have a coil that is ready to be stacked on the lamination to mount the machine. And this casting process offers some advantages in terms of the electric behavior of the machine. So, first of all, the geometrical advantages. By the casting process, we have the possibility of the precise reproduction of the constructed geometry. So we can construct the coil and can realize in every conductor every cross-sectional geometry that we want. And we can use this to increase the slot filling factor. We can realize slot filling factor of up to 90%. And additionally, we do not require a bending radius at the end windings, so we get a very short machine. And further advantages are from the geometrical side that we can realize innovative cooling concepts. Perhaps we can increase the length of the end windings to reduce thermal hotspots, or we can integrate cooling channels in the conductors. So with casting process, we have very good geometrical flexibility in the coils. From an electromagnetical point of view, of course, the biggest advantage is the slot filling factor. We have a reduced resistance compared to a wound coil with same outer dimensions. So we can use this to reduce the slot height of the machine, to reduce machine weight and material costs. Furthermore, the flat conductor arrangement leads to reduced current displacement effects. We see that on the right side, we have a comparison of 2 coils with same turn number. One with a flat conductor arrangement, one with a round conductors wound. And with the flat conductor arrangement, we get from an electromagnetical point of view the optimal arrangement. So we have very low current displacement effect compared to normal wound conductors. And of course, the bending radius at the end windings from the electromagnetical point of view has some advantages too. We increase or we get the possibility to increase the distance from the housing, so we can reduce eddy current effects in the housing due to less leakage fields. And additionally to the electromagnetical advantages, the flat conductor arrangement of the casted coils offers some thermal advantages. Again, the flat conductor arrangement leads to very good heat flow from the coil to the lamination stack. We did some measurements to quantify this effect. And it came out that the thermal resistance of a casted coil with a one-dimensional conductor arrangement can be decreased by about 80% related to a wound coil. So we proved in some measurements that continuous current density in water-cooled applications of 24 amps per square millimeters can be realized. So all in all, the combination of the high slot filling factor, the excellent thermal behavior, allows to double the current density in the slot area. So the current density in the slot area is the most important value to increase power density and torque density of electrical machines. We can realize these coils in different casting processes. The most suitable process for prototypes and small series is the investment casting process, also called lost wax casting in literature, for small coils up to 200 millimeter length. We can realize conductor heights down to 0.8 millimeters and conductor areas of 4 square millimeters. For very big coils, we can realize lost foam casting. It's another casting process based upon lost models. We can realize coil lengths up to 800 millimeters, areas about 20 square millimeters for very big coils, for example, exciter coils or large DC machines. We are able to realize coils in different materials. In copper, we realize conductivities of 46 to 47 megasiemens per meter, and in aluminum, we realize from 34 to 36. The insulation of the coils is afterwards done by different processes. We can use EPD processes or powder coating processes, depending on the wanted layer thickness. With powder coating, about 40 micrometer, with EPD processes from 20 to 30 micrometer. And we can realize insulation strength of about 2 kilovolts with 180 degrees temperature stability. At the end, I will give 2 application examples we are developing at the Fraunhofer Institute. The first one is we use the casted coil in the development of an air-cooled wheel hub motor. So we use the advantage of the high slot filling factor and the reduced current displacement effects and the good thermal connection to the elimination stack to realize a machine that is water-cooled using aluminum as a raw material for the winding, without a decrease of power density compared to a wound copper machine with water-cooled, in a water-cooled application. The realized coil has 15 turns, a conductor height of about 1.5 millimeters. We increase the length of the end windings to reduce thermal hotspots, and the length of the coil is about 60 millimeters. This is a Fraunhofer project where we realize the machine, and we will test it by the end of the year and publish test bench results of this machine. For the first industrial application of the process was realized in collaboration with the Bremer Lloyd Dynamo Werke. We realized a coil, a commutating winding of a 470 kilowatt DC machine. And in this concept, we realized an innovative cooling concept. We used the geometry or the geometrical flexibility of the coil to realize axial cooling concepts. So we had an air-cooled machine and we were able to replace a wound copper coil with an electrically equivalent aluminum coil. Could therefore reduce the weight of the machine and the raw material costs, and at the same time we realized the reduction of the temperature rise of about 30 Kelvin in continuous operation. So this was the very first industrial application of the casted coil process. As a conclusion, the cast coil process offers high slot filling factors up to 90% due to the optimal fitting in the machine. We can reduce the bending radius, so we can realize no bending radius to better utilize the lamination stack. And furthermore, we have a good thermal behavior to double the current density per slot area. In the next steps, we will do further research on the process development for highly productive casting processes. We want to produce the coils in die casting process to reduce costs and to realize really cheap coils. And we will adapt the process to distributed winding systems to realize distributed winding systems with casting coil process, with high slot filling factor and good thermal behavior. Thank you. I think the discussion of the presentation will take place afterwards. I will give the word to my colleague, Mr. Siebert.
Thank you, Alex. Hi and welcome, ladies and gentlemen. I'm glad to be here to present you today a new and outstanding manufacturing technology for electrical machines. The headline of my presentation contains two important topics: laser processing and magnetic properties. Therefore, I'm going to present a laser cutting technology for stator and rotor lamination, as well as an additional surface treatment in order to recover manufacturing-related magnetic property deterioration. My presentation will be short and compact, but before I come to the content of my presentation, I just want to say a few words about the institute I'm with. I'm with the Fraunhofer IWS, which deals with applied research in the areas of laser material processing and surface technology. Here I brought you some facts and figures. It's worth to mention that 50% of our revenues has got an industrial background. This is important for not losing sight of relevant industrial questions and problems. Core competencies cover a wide range of technologies such as optical characterization, sensor and measurement technology, as well as manufacturing systems. But now let's come to the actual presentation. First of all, I start with the motivation. Here I'm going to explain why this new manufacturing technique is so needed, and followed by the process characterization. We will have a deeper look on the process principles of laser remote cutting in comparison to laser fusion cutting. Afterwards, the results in terms of cycle time comparison, cutting edge quality, and we also will have a deeper look on the magnetic properties. And at the end, conclusion and outlook. I assume that every electrical machine manufacturer will always tell me that the production of efficient electrical machines is still too expensive. Of course, a lot of work has been carried out in terms of reducing the costs, but in my opinion, there's another important issue: flexibility, especially in days of changing markets towards more customized products, customized electrical machines. Having a certain flexibility in your production system might be a key advantage. And as well, magnetic properties are also an important issue to fulfill the requirements of supreme efficiency classes. In the case of cost reduction, usually the mechanical punching is used for large-scale production rather than for prototyping and small series due to high tooling costs. On the other hand, laser cutting is favorable in terms of prototyping due to a high flexibility of processable material grades in terms of gauges and component sizes. I think here we need a manufacturing technique that combines these two advantages. And laser remote cutting is supposed to close this gap between these two techniques because it's wear-free, it's contact-free, it's flexible, scalable, and has got a higher break-even point, or has got a break-even point at higher batch sizes. So, but how does actually laser remote cutting looks like? Let's have a look on the process principles. We start with the laser fusion cutting. A conventional cutting machine consists of a cutting head with a nozzle having a certain standoff to the workpiece of between 1 and 2 millimeters. When the focused laser beam strikes the material, the whole volume of the cut curve is heated up, molten, sometimes vaporized, and driven out by the gas jet. We call that process piercing, and due to piercing, we see a large heat-affected zone around the cutting curve. Once you apply a certain feed rate, then we see this typical striation on the surface of the cut curve with more or less burr on the backside of the layer, depending on chosen process conditions. On the contrary, laser remote cutting utilizes another process principle. The idea here is to vaporize the material with as little melting as possible. Here we don't melt the whole volume, just let's say between 5 and 15% of the thickness. The laser beam creates high pressure in the molten area with vapor that expels the molten material from the cut curve. And so the cutting is done in several cycles. Due to this gradual ablation, we just see a very small heat-affected zone. And unfortunately, there is some burr left on the top side of the layer. But with an additional burr removal, it's possible to remove that burr and to modify the shape of the cutting edge. The cutting is actually done with a scanner that deflects the laser beam very fast. For one cycle, you can reach cutting speed up to 600 meters per minute. And in order to analyze cycle times, we did a cycle time comparison with the laser fusion cutting. Here we used an exemplary contour from a real application. This data tooth is shown in the figure with high complexity. Just to give you an example, in that case we used 10 cycles for cutting, 3 additional burr removal cycles, and we applied 18 additional laser striped lines. The idea of this surface treatment is to modify the residual stress state within the lamination. For example, punching induces tensile stress in the lamination, and if we apply a surface treatment strategy that induces compressive stress, then we can reduce this tensile stress, which results in an improvement of the specific core losses. In order to determine the cycle time, we did slow motion filming and calculated the cutting speed, the average cutting speed, and the cycle time. In that case, cycle time was 0.4 seconds with an average cutting speed of more than 15 meters per minute. The cutting itself just 0.3 seconds, burr removal 0.1 seconds. the laser fusion cutting was done with a conventional cutting machine, well known in industry and applied for cutting stator and rotor laminations. Here we retrieved from the access drives the signals. These signals tells us exactly where each drive is, or at a function of the time. And so we can calculate velocity, accuracy, and cycle time, cutting speed. However, let's see how laser remote cutting works. This is real time. And now again in slow motion. The treatment itself needs additional 0.4 seconds. A very fast technique. So now let's come to the geometric characterization. Here I brought you to cross-section for laser remote cutting on the left-hand side and mechanical cutting right-hand side. I chose this example, material grade was 0.5 millimeter, because for thicker gauges there might be some problems for laser remote cutting. But let's start with the advantages. Mechanical cutting causes this burr at the back side of the lamination. There is no burr for laser remote cutting due to the burr removal. But if you process thicker materials, we see a slight wavy shape of the cutting edge. For thinner materials like 0.35 millimeters or NO20, NO10, that is not an issue. Of course, you can get a more smooth cutting edge if you decrease laser power, increase the cycle, but that also decreases the output performance, cutting speed. I'm telling you that because you always have to adjust your approaches according the product requirements, output versus tolerance requirements. And the same holds for the magnetic properties. Here on the left-hand side, I've shown various manufacturing techniques. The black line represents the annealed state. And laser remote cutting achieves a very good magnetization behavior, followed by the guillotine and conventional laser cutting, regardless of chosen laser beam source, gas laser or solid state laser. On the right-hand side, I wanted to show how flexible this process is. You can adjust your process to achieve perfect magnetic behavior. Then the cycle time is the same as conventional cutting, or you can increase the cycle time, but then you will have just the same magnetic properties as conventional cutting. Same holds for the specific core losses. Here again, remote cutting achieves pretty good results. The question now was, maybe we can have a process with the focus of high output and improved properties. And so we tried that laser surface treatment in order to modify the stress state in the laminations. And in the lab, we achieved an improvement of 10% specific core losses. Of course, this process is very suitable for a cutting process with the focus of output. That means the higher the magnetic property deterioration, the higher the possible improvement you can achieve. So if there's no magnetic deterioration in the material, of course you cannot improve the properties. So now let me conclude a few points from that presentation. Today, I showed you a cutting technique that is 2 times faster than conventional laser fusion cutting. It's a very flexible technology in terms of material grades, gauges, as well as you can adjust your process between perfect magnetic properties or output, there will be no burr on your laminations. This technology is perfect for serious production. And furthermore, I presented you what we call the laser healing technology in order to modify the stress state in the material. This technology is easy to implement, but there's one more point. We want to transfer these results into industrial practice. And that's the reason why we have a project together with the colleagues from the other Fraunhofer Institute. Here we build up a motor wheel hub, and the conventional cutting has already been carried out. The next step would be to improve conventional cut stator lamination, and the third step will be to manufacture a stator with perfect magnetic properties. These laminations, of course, will be bonded, assembled, and tested at the Fraunhofer IFAM. So, thank you very much.